Hi, welcome to the next part of this video. In this video I would like to understand a bit more how the address mappings work, how they are mapped to the device tree. There is a video I'm currently watching, this one, Device Tree for Dummies, and what this guy does is he has, for example, the I2C bus and he has it mapped to some address, and I just want to understand how for the Agilex 5 this whole SoC is done, and I hope you will enjoy it. Okay, now I opened QSYS, the golden hardware reference design of the Agilex 5 example here, and what I can see is okay, strange. There is an overlapping address space. Why? Okay. Because this address space and this address space, some addresses are overlapped. But okay. What's that? That's the periphery. These are the GPIOs. Okay, that makes sense. And this is the video bridge. That's also okay. Now, what is here? Nothing. What is here? Nothing. Yeah. Okay. What's that? These are the interrupts. Yeah, and we can also understand how the interrupts are mapped later, because if, for example, this interrupt number 4 does something, our HPS, the processor, the Linux has to understand, okay, that's interrupt number 4, okay, this means blah, blah, blah. We also have to research on that later. Good. But now, let's dive into this thing. I clicked Control Shift and then D. And by clicking this button, I can zoom out again. Okay, this is the address of the fabric to SD-RAM. The fabric to SD-RAM. Fabric to SD-RAM adapter. Memory map match. Okay, this is the JTAG adapter to directly do some analysis. This is the bridge. This is something that goes to the outside bird. Let us quickly understand again what this was. I did that already, but I forgot it. Okay, zoom out. Open. Fabric or FPGA to assume. I don't know what this is. Let's click here. This is a master, meaning, okay, this controls slave, then F to this. Okay, this goes to this goes directly to this one. Okay, that's strange. It goes to the HDMI thing. Okay, here I have my. Okay, this is again for debugging purposes. What's that? And this is the lightweight HPS to FPGA. Okay, interesting. F to SD-RAM. I had a document. Let me open that. HPS to fabric, F to SD-RAM. Okay, this is something. This is a port from the FPGA fabric through the NOC. It is connected to the HPS. No, from the fabric through the NOC, it can go to the DRAM. Okay, and in this architecture, what this thing does is Aha, it is the HDMI master. Aha. Okay, what this does is getting the HDMI data, I guess, doing something inside with that data. Yeah, HDMI. This is the signal, HDMI. What's that? Slave AXE. Okay, I guess this thing then does the read out. What's that? Okay, this thing I guess does the read out and then pipes it here. And this thing does then the write operation to the F2S DRAM bridge, which is part of the HPS block. And here we can see this thing goes to the HPS block. This yellow thing should be including this red thing, but okay. Goes to the HPS block, and from here it goes to the DRAM. Good. And if the HPS wants to read it, what the HPS can do, it can just through the NOC do some read operation through the CCU and get the information. Okay, understand. Yeah, very complicated, extremely complicated, but okay. Okay, got it. So now again, addresses. These are the addresses. For example, how do they map the address of the UART? Because the UART, as we saw in the last video, is part of this HPS-IO. And how does the kernel understand what the address of this thing is? Okay, there is no address mapping because this UART, let me see here, UART here. This is some internal thing. But still it needs some address because the processor needs to address something and then pipe the data into it. But how do they do the UART thing? Okay, let me open the terminal. Let me show what is here, projects, and then number 2. Good. Now I should find files I need to find files that are device tree files and include Agilex 5 in the text. Let me open my friend ChatGPT. ChatGPT. How to search for a file that includes the string UART and has the string Agilex 5 in its name and has the file ending. No, that's okay. I hope it's intelligent enough to do it for who on. I hate Windows. Okay. Finds path to search. File name includes this. Exec. Why is it exec? This will run the grep command on each file found to search for the string UART inside the file. Why it doesn't? Is it possible? Is it possible for Ubuntu to use the pipe operator instead of exec? Well, I will try this now. Yeah. Path is trusted firmware. It's Linux SoC FPGA. Do the search here. Okay. Thanks for nothing. I always put some D in front to not execute the commands, because otherwise sometimes some commands wouldn't be executed. Okay. Also print in the terminal the search result. Yeah. I know what I could do. Okay, let's try this one, and then I already know what I could type in. Okay, that's okay. What does it do? Find type F name Agilex5 print 0. Okay. Let's open some music. Okay. Good. dtsi, this is part of the video, indicates some intermediate thing, and this thing indicates the drivers. Okay. FPGA-SoC Agilex dtsi. This is the Agilex5-EAGLE board. Here's the Eagle board. This is the top level DTS. Let's open it. What's that? Drivers, clock. Okay. Choosing standard Quartus. Is this the address? Let's ask our friend ChatGPT. Yeah. Base address. Okay. Who defines that base address? Let's search for this base address. Let's search for this base address in the kernel. No, but this is the arguments. But now let's search for the space address in Quartus, if there is some mapping or something inside of Quartus. Let's go back and then change to this. Search for this, but you can do grab -R, this, and also remove this one. No. Let's search for this. Maybe there's okay. Let's search for that. Let's search for UART. No, but UART exact string. How to search what grab for exact string match. There we go. Recursive exact. UART interrupter locate. This is the ticket script, yeah. UART inter. Open this one. Aha. UART base. Interesting. We have here UART base 1010, and in our device tree we had something different. We had this in our device tree 10C. I have an idea. Is there a way to print in Linux kernel the base address of the UART port? Using the, if your platform uses the device tree, yes. Yeah, I know. Oh, wait a minute, this is a different one. What does this thing do? Is this thing executed somewhere? No. I guess this file is nothing. Oh, I have an idea. What if I dive into this thing and then I open this thing? Maybe I have here some configurations. Let's search for UARTs. Input delay. No, this is interrupt. You have zero interrupt. And I want to. Because, okay, I tell to the device tree, hey, listen, at this address you can use the UART. That's great. But somehow the HPS needs also to know about that address. You know, and the question is where I do map this. Because this address could also be an address to something. And this is something I cannot see here. And I don't like it. I will search for this with some other. What I could do is documentation. Haha. Maybe here it's something. Let's open this friend. No, this one. UART. Okay, I will write a question to. And then I will try to understand it. Okay, I've now started a research with some friends and also with colleagues inside the work on how this thing works. So basically the question is, this is our UART. Good, I understand this is our UART. And according to the device tree file, this thing listens to this address. Good, that's also something I respect. But how is the mapping done? So how do we know that this thing has the address? What was the address? 10C blah blah blah. In Quartus, I couldn't find this information. I did some grabbing. I found out this script, but this script looks like not relevant. What I could do is maybe here is something written. I don't think so, but let's see. What's that? Okay, that's something different. Also, this is something generated by the wow. Okay. Mm-mm. Okay. Let's see if I get an answer on this issue. I will then record it. Okay, now continue. How does the kernel... Okay, let's start our program now. Let's close this. I want to understand how the kernel communicates with the UART stuff. Close this. Hey, I could, and I also want to understand the DRAM access. I would like to understand, yeah, I want to do some signal scoping. I would like to add some signals here to scope the signals. You know, I would like to dump the RAM. I would like to dump the whole RAM. And maybe I can do this with mmap. Okay, let's first start with the program. Okay. Huh? Auto detect. Yeah. No. Okay. Start. Failed. Delete. Start. Stop. Ah. Yeah. No, I just stopped the boot process. Yeah, that's the address. What was this again? They really want to annoy someone. State of out. Ah, yeah, generic interrupt controller. Did the message? Yeah, okay. Yeah, interrupt 21, 21. Is this somewhere in the device tree? No. it might be the case this is something defined by the Agilex 5 development team, and this is written nowhere. Let me open this thing. This might really be the case. Intel Corporation. Yeah. Yeah. Everything is here. Right. You at 1, you at 0. Okay. I think what this guy did is, like the person who built the Agilex 5 board support package, and I guess I know this guy. I don't know if I can name him, but I guess what he did is he either copied the Agilex 5 device tree I files, this intermediate file, this is a drive device tree something intermediate configurations, and this is not written in Quartus at all. This is fixed at that address, and if you want to work with the Linux, then use this file and build up your stuff with that, I guess. I guess this is what he did, but I wrote him an email and I asked him for input on this, and then I will also share the feedback on that email. But this is what I think now. And everything has here fixed addresses. Okay, now let's open this file. Wow. Aha. Include this one. Okay. Because it just takes the viewer zoom and it doesn't do any further configuration because the configuration is here. Yeah. That's how it works. Okay, we've got it. Yeah. Okay. How it works is, and this is by the way also described in that video, in this one, in this guy, he describes it somewhere here. Let me try to find it. Let me try to find it. Here. It takes one file and then another file and it compiles down to a DTB file. And here you have the include blah 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 .dtsi, and these two things, like the BeagleBone board here and the internals of this SoC, are then compiled to a system on chip. And basically what is done here is the same. We have the dtsi of the Agilex 5. This is something delivered by Altera, Intel Altera. and this is then combined to that thing. And what here the Agilex 5 only does is taking this thing, defining some boot arguments with the parameters that guy already knows from this file, and then pass it down to yeah, compile it and then build the Linux. And now I'm just wondering how we did the compiling stuff. Let me see, projects. I have here my script. Open that. .dt something. Yeah, what is this? Create the Linux kernel and include this one. And this thing includes this thing. Yeah, it's that folder. This thing. Let me see if it's really that. SoC Agilex5, yeah, that's thing. This thing, and this thing includes this file dtsi. Okay, what's that? And that's the Linux kernel, the configuration. What the kernel should be able to do. You can, configure the kernel, what its features are, if it should use some special features or not. This is what this is. Okay. .dt. What's again here? What's that? Copying DTB in kernel. Okay, this is our DTB we've built. Device tree blob. This is the device tree blob. This is a binary file where it is. This is in the Linux folder. It is in the kernel ITB file. Let's open kernel ITB. And this should be, yeah, that's binary. But what we can do is get that path and then change here and ghex soc. And here we have the hexadecimal version of that. And is here such function? Yeah, UART. UART. String was not found. UART. Here. There is this information. Cool. These are the boot arguments. By the way, once I did a hack boot. Okay, it's not here. But yeah, I will not. Yeah, I will not say it. Good. Okay. That looks good. Now I just want to continue my search. Okay, that's it. Good. That was pretty interesting. In this video we understood how the mappings are done and the kernel, and this is what we saw here. And in dmask we had also the same address. Like if I go to dmask again and if I say grab this thing, and I can see, yes, the kernel takes that information, the kernel maps it there. Is there some way of doing how to directly write to the address x via bash in Linux terminal, to the physical address, not the virtual, to the physical address. Okay, if I write to this address, what basically should be done, it should pipe that to the console. So I should see it in the console actually if I do this. And the address, I could compile using mmap. Daemon. Yeah, this should be enough. You know, I add the D in front of it, then it doesn't execute it immediately. I have this here, we don't have sudo devmem. It is 10c02000, right? And now I should see that beef. Ah, I don't have that. Echo to devmem. Do I have this? Yeah. How can I directly... Let's ask our friend. Change this command to write it directly to this address. 0x10c0. Ah, no. Ah, nice. Echo outputs the byte which is piped into DD to write. Oh my god. Oh my god. If this works. Echo. Let's write that beef. Right. How to write to a physical address via yeah, but I could do this, but I don't want to write the C code, compile it, and blah blah blah. I want to use the terminal. Space in terminal. Let's see. Ah, okay, doesn't work. I will stop recording now. Good. Okay, we understood how the device tree files work. I will continue my research and keep you guys posted.